Today we want to talk about capacitors. Almost all capacitors follow the same sort of construction, where we have some kind of metal plate and another metal plate that's identical, and they are separated by some kind of insulating material, which is often referred to as the dielectric. So you've got a metal surface, and they're separated by an insulator. Capacitors can be used to store energy. Basically, if you put this into a circuit, you can add electrons to one side, remove electrons from the other side, and it starts to have a voltage from one side to the other. Now, how many electrons you can squeeze on without the voltage going up too much is based on how much area is available. So in order to make bigger capacitors, they often have to make these plates much bigger. And that's why we often see capacitors in the shape of a cylinder, where the layers of metal have been rolled up. So construction like this is common, and that's why on page 1 we saw lots of cylindrical shapes like this. So although real capacitors look like this often, we will always use the idea of the theoretical type capacitor, that has this imaginary big flat plate, this other imaginary big flat plate, and this gap between them. In this video we're going to look at the practical aspects of working with capacitors, charging them, discharging them, plotting graphs of voltage and current as the capacitors charge and discharge, and seeing what information we can extract from those graphs. Here we have a simple circuit to help us charge and discharge a capacitor, and as you can see we've got a double throw switch here, so the switch stays connected here, but it can either be pushed to this A position or to this B position, and you can see the capacitor's here. This is our symbol for a capacitor. If we switch it to the A position, then the capacitor is connected to the voltage source and it will get charged. When you switch it to the B position, then it will discharge. Now if we want to investigate this, we don't want it happening instantly. If we want to investigate how long the capacitor takes to charge, we want to put something in that will allow it to take a bit longer to charge, so we can observe what's happening using a voltmeter. So we introduce a voltmeter in parallel with the capacitor, and then we want to introduce a resistor. Now where we put the resistor depends on what we want to do. So again, if we identify this side as the charging side when we've got the capacitor connected to the voltage source, identify this side as the discharging side, then one of these will be the slow side if we put the resistor on that side. So if I take this resistor and put it on the charging side, then it will take a long time to charge. So when I switch this to A, there'll be a long process of charging the capacitor, and we can make it even longer by increasing this resistor. When we flip to B, that will be an almost instant discharge because there's no resistance in this circuit. And so if you were investigating charging, you would set it up like this. If, however, you wanted to investigate discharging, then you would just move the resistor to the discharging side. What happens now is if we press the switch to A, the capacitor will very quickly charge. When we flick it to B, it will discharge quite slowly through the resistor. And this is what we tend to want. We want the resistance on the side we're investigating. So if we want to investigate charging, we put the resistor on the charging side. Want to investigate discharging, we put the resistor on the discharging side. And so whichever side you've got it on, for this, for example, we'll have slow charging in position A and rapid discharging in position B. If we move it to here, then we're going to have rapid charging in position A and slow discharging in position B. So let's say we're investigating charging then, so we put the resistor in the charging side, and what we would do is we would leave the system in position B until we were ready, and then we would check that our voltmeter is connected properly and that's giving us a reading, and then we would start a stopwatch, and then we would just start recording the voltage at equal time intervals. Now the actual time intervals you use depend on the values of R and C, and there are ways of calculating values of R and C that will give you reasonable times that you can get the experiment done in. Obviously if R and C are really high, the experiment will take a very long time. If R and C are really low, it will take such a short time that you'll not be able to take results. So RC is the time constant of the capacitor circuit. The product of R and C gives you a time, and it's the time for the capacitor to charge to about 2/3 of its full value. So in order to use this kind of table where we're going in 20-second intervals, we would need to be able to sort of have the value of RC maybe round about 100 seconds. So we've got a reasonable amount of points before it hits 2/3 charged. And we can do a calculation for that. So let's say we have a capacitor of, say, about 1,000 microfarads. Then we can use that as a basis for trying to figure out what resistor would give R times C equal to 100 seconds. So if we want RC to equal 100, then R is going to be 100 over C. And that's going to be 100 over 1,000 microfarads. And that gives us a resistance of 100,000 ohms, or 100 kiloohms. So this circuit would now be suitable for the table I have drawn up. Okay, so as I say, you put it to the discharge position to empty out the capacitor, that's position B. Then you flick to A, start your watch, record your initial voltage, which will be nothing, and then when 20 seconds comes along, record voltage again. When 40 seconds comes along, record voltage again. And you may need to pay a lot of attention to the voltmeter, and if you have a practical partner, get them to count you in. You know, when it gets to 17 seconds, get them to do a little 3, 2, 1 and read, and then you call back to them the voltage, and when it gets to 37, they again go 3, 2, 1 and read, and that'll give you nice, reasonably accurate values of voltage. And you keep doing that for a few minutes until there's very little left to go on to the capacitor. In other words, when it's very, very close to the voltage of this charging system here. So let's say you've got this set at 6 volts. Let these run for a while, and when this is getting very close to 6 volts, then you're pretty much done and you can leave it there. If you wanted then to do a discharging, it's very, very similar. We just move the resistor down to the bottom here, move the resistor down to here, and that becomes then a slow discharging circuit. So you flick to A to charge, flick to B then to discharge. Okay, I can't move my resistor at the minute because it seems to have locked itself onto the diagram, so I'm sort of stuck with it in that position. And so we'll just imagine if I took this resistor from this part of the circuit and moved it down here, that would become a slow discharging, fast charging circuit, and we could then do another table, exactly the same setup as we've got now, because we're not going to change R or C, and whatever this voltage is, that's going to be your starting voltage for the charged up capacitor. When you charge it, you'll see this voltmeter rise until it reaches this value, and that you'll be starting with a high voltage of whatever this charging voltage is, and then when you switch the switch over to the other position and start your stopwatch, that voltage will start to decay over time. And you do the exact same method, get your partner to call it in, 3, 2, 1, each time it reaches a round number of seconds that you're waiting for, and you should get a nice set of voltage values for discharging then. So what graphs do we end up with if we plot voltage versus time? Well, for charging, you'll get something like this with voltage up the side here, time along the bottom, and the voltage on the capacitor increasing, and it will eventually flatten out at whatever the charging voltage is, whatever your battery or power pack are set to. So if your power pack's set to 6 volts, this will flatten out eventually at 6 volts. If your power pack's set to 10 volts, this will flatten out eventually at 10 volts. So you've got voltage up the side, time along the bottom. So that's what you end up with when you're charging. So what about discharging then? What does it look like? So now we get the voltage coming down as the capacitor discharges. So we've got one that's rising to the charging voltage and one that's falling from the charging voltage. Okay, so this one's going to flatten out at 0, and it'll, as it gets less and less charge, it will go flatter and flatter there towards 0, whereas this one's flattening out towards whatever voltage you had the charging circuit set to. So you can imagine these are both the same position. Where this is heading to is the same as where the discharging one is dropping from. Now, if you wanted to plot the charge on the capacitor, these voltage graphs are easily converted into charge graphs because Q, the charge, equals CV. So if you took your voltage values from the previous example, and you just take those values and multiply by the capacitor value, you can get a set of Q values. So the act of multiplying by C will convert a voltage column into a new column that you can call charge. And then you can plot again with charges. But Q will always follow what the voltage graph is doing because Q equals CV. This is always going to be the case. So you could replace the voltage axis with a charge axis and the graphs would look the same. They might have slightly different scales, but they would be the same shape. So voltage graph and the charge graph are always doing the same thing because they're proportional, because Q equals C times V. Now the current graph is unique because it always descends. It doesn't matter whether you're charging or discharging, current always starts high and ends up low. So although the voltage is rising during the charging phase, the current's falling. So I'm going to try and explain why the current graph is always a decay curve like this. We'll look at the discharging because it's easier to explain. We'll look at it first. So during this phase we have already charged the capacitor and we've moved it to this position. So once we are discharging, we can ignore the top half and just think of the capacitor as being a voltage source. So it's behaving like a cell and it's driving current round this loop. Now we know what the voltage graph is doing. It's falling. So the value of the little imaginary cell that the capacitor makes is not a constant voltage. It's a falling voltage, so it will create a falling gradually current. So as current comes around here, gradually neutralizes the charge on the capacitor, the value of its voltage decreases, and so from Ohm's law, V equals IR, we're going to get smaller and smaller currents. So that explains why as the voltage comes down, when you're discharging a capacitor, the current also comes down. So we've explained what's happening in the discharging side. So why does it still come down when we are charging? Now, when we're in the charging phase, this bottom bit is just for emptying the capacitor, discharging it and allowing it to neutralize. So during the charging phase, we can ignore the bottom bit and just concentrate on the top half. So what we've got here is a fixed voltage which will drive current in this loop, and basically what will happen is this positive side will take electrons off this side of the capacitor. This negative side will deposit electrons onto this other side of the capacitor, and the capacitor will start to charge. Now as the capacitor gains a voltage during the charging phase, that voltage will oppose the voltage that's trying to put charge onto the capacitor. So the voltage on the capacitor is increasing as we charge it, and that creates a pushback against the fixed voltage of our charging circuit. So let's say we've got this set to 10 volts. That means that the capacitor voltage is gradually creeping up to 10 volts, and it will oppose a tiny amount at first, so you get lots of current, but it will start to oppose more and more and more as the voltage on the capacitor gets closer and closer to the voltage of the power supply. Eventually they will become equal, and so the push in both directions are equal and opposite, and that's when the current will stop. So initially there's nothing on the capacitor, so you get loads of current initially, but as it starts to charge, it pushes back harder and harder until eventually the current stops. So this one, it's a voltage that's driving the current, but the voltage itself is decreasing. Here it's like a fight between two voltages, whereas one that's fixed and one that's increasing, and eventually the two become equal, and that's what stops current in the charging circuit. So if you're asked, and later you may be asked to find what we call time constants, where we want a decaying curve, your top tip is, instead of doing a voltage experiment, to put an ammeter in line with the resistor and do a current experiment, because even if you got the circuit wrong, the current always comes down. So if you've accidentally drawn a charging circuit, it doesn't matter, the current still comes down. If you've drawn a discharging circuit, charging circuit, and you're trying to do this with voltage, then you need to make sure you're doing this one, okay? Because the charging circuit creates an increasing voltage. So if you want a decreasing voltage, you need to be on a discharging circuit. But the beauty of the current graph is that it doesn't matter which circuit you are using. If you've got an ammeter in series with this resistor or in series with this resistor, the current will always fall. And so you can guarantee yourself a graph of this shape, which you can get a time constant from. One of the most common things you'll be asked to do with a capacitor graph once it's done is find a time constant. Now, a time constant is defined by the SIA specification. Well, if I'm honest, it's not defined in the specification, but we're told to define it. Thanks, SIA. And we use the value that the voltage will fall to 0.37 of its original value in one time constant. Now, what does that mean? So this voltage here starts at a value. If we find 37% of that original value, then we will have found the part of the graph where one time constant has elapsed. So you can see it takes 10 squares. So we're looking to put a marker in at about 3.7 squares. So 0.37 of the original voltage is going to be about there, and that corresponds to this major line on the time axis. So if we start at this value V0, by the time we've reached 0.37 of V0, one time constant will have elapsed. So by marking in 0.37 of V0 and figuring out how long this is, by reading it off the time axis, we can read one time constant. Not only that, but you can repeat this process by picking, say, a different starting point and finding 0.37 of that, and again, the time elapsed between those two locations will be one time constant. So it's possible to measure this more than once and take an average to improve your accuracy. Hopefully you found this useful in helping you to understand what's going on in the practical investigation of capacitors. We also have another series of videos talking about the physics of what's going on when you charge a capacitor using a model involving the flow of water. In that system, we imagine that a voltage source is a big infinite pool of water, and that a capacitor is a little smaller container that we can connect that voltage source to. What happens when we connect it is that water flows from one side to the other in much the same way that charge flows from the voltage source to the capacitor, and some people find this description very helpful. So watch out for those videos because they're quite good at helping you to get a feel for what's actually happening when this microscopic invisible stuff is going on. You know, it's hard sometimes to get a good picture of why things do what they do, and this model seems to work quite well at explaining it. Okay, so thanks very much for watching.